You can see there's no operator there, so that means you're basically all those states are empty in that case. And what about for the superconducting scenario here? This is going to be hand waving because it's kind of a pain to go through and do the variational calculation. That'd just be like a whole other course or a whole other class. So what happens, remember what I said before in the case of the superconducting scenario, is that because the field Fermi C is unstable, the idea is that, well, we have some kind of interaction between the electrons that's actually attractive, let's say for states near the Fermi surface. And so what happens is that the Vk gets smeared out. It looks like a thermal smearing, but it's actually not. It's like a coherent. It's actually very coherent because you have that phase factor. So even though it looks very similar to what you have with just like a Fermi, thermal Fermi factor, the Vk ends up looking like this, but it's a very coherent process, so that you're pulling some of the pairs outside and you're putting them out here. And then, of course, in order to normalize everything, also you can point out that UK, for normalization's purposes, that this has to add up to 1 at all times. And then, so the UK ends up looking like that, then for the superconducting scenario. And so the idea is that you have some amplitude that below the Fermi surface, the states may be unoccupied, some coherent amplitude, and then above the Fermi surface, the states could be occupied in the case of the superconducting ground state. And that's going to be kind of sketching things out and then giving some hand-waving arguments. And if you can actually, if you find a nice book, I don't know how good Schrieffer's book would be, well, at any rate, or something online. I don't know if there'd be something online that you could find that maybe to help you kind of giving the explanation. But anyway, the key idea is that one of the things that makes the superconducting scenario more interesting than just, let's say a Fermi gas at finite temperatures is that the Fermi factor is completely incoherent, but here, these guys are actually related to each other by that macroscopic phase for the superconductor. So like the ratio of Vk over Uk ends up being e to the I times the phase factor that comes into play in that macroscopic superconducting wave function. Now there's again a whole mess of either quantum field theory or many-body physics that one could go through to try to give more than just kind of the hand-waving explanations that I'm giving right now. But at any rate, there are a lot of things that make this a really intricate, very, very amazing and intricate ground state. And and the other thing that I'm going to just mention one more time is that if you were to attempt even to write down, let's say, the field Fermi C using the old wave function formalism, it would be a nightmare. It would be an impossible nightmare because remember I mentioned that you have to take this humongous 10 to the something power, 10 to the 20 something power by 10 to the something power matrix, take the determinant of that matrix, which is called the Slater determinant. We have the psi1 of x1, going all the way across to psi1 of xn, and down in your bottom row you have psi n of x1 going all the way to psi n of x to the n, xn. And then you're taking this gigantic determinant of this humongous matrix. And so not only would it be difficult, it would be absolutely impossible to do it. So that's why using the formalism involving these fermion operators, you can see is not only a much more powerful approach, but it's actually pretty much essential once you get to these types of many-body systems in quantum mechanics. And so it's kind of amazing that you can, just really on a postcard, you could actually write down the BCS ground state for a superconductor, for example, for all these particles. The number of values of K is humongous. It's comparable to the except for the spin it up and spin down, it's basically comparable to the number of particles, or well, it is equivalent to the number of, if you just go out to KF, it's equivalent to the total number of pairs in the system, or the number of electrons in the system. And so at any rate, it's kind of a powerful formalism. I wanted to give you just a bit of a flavor for it without necessarily going through and saying, okay, now we're going to do the variational calculation, try to minimize the energy, blah, blah, blah. What I will do on one of the upcoming homeworks is I'll probably give you a simpler variational. I'll try to introduce the variational method, but I'll give you a much simpler single particle quantum mechanics problem involving the particle in a box where you do a try. But again, what's the basic principle? So what BCS did is they say, okay, let's use this as some kind of trial wave function right here. And then, but how do we figure out what U and V are? And so what the idea is that from a conceptual point of view is I concoct some parameter, some way of parameterizing it. And it turns out that the way Tinkham does it in his book on superconductivity kind of simplifies things a little bit further, because we sort of introduce this other parameter to guarantee that this condition is always satisfied. But at any rate, they go through and they end up kind of showing, okay, this is what these guys are going to end up looking like. They also end up extracting this thing that we call the BCS energy gap, showing you that there's actually a new condensate where there's some minimum energy required to create what we call a pair of quasi-particles, where you have to overcome this BCS. It's like, roughly speaking, you think of it as the energy required to break a Cooper pair, more or less. And so there are a lot of things that come out of the BCS theory that would take, again, a much more advanced class to get into the details about it. But conceptually, in the original BCS theory, what they were doing is saying, well, this is going to be our trial wave function, more or less, our trial ground state. And then what we do is we take a variation and set that variation equal to 0. It's like a max-min problem to try to figure out, okay, what do these guys have to be right here? So what I will do on one of the subsequent homeworks is I'll give you a problem where I'll give you a trial wave function for a modified particle in a box, where I say, let's say we have a particle in a box scenario where I add a little bit of extra delta function perturbation inside the bottom of your well. And now I give you a trial wave function with some parameter. And so what's going to happen, you'll take the expectation value of the Hamiltonian. In this case, it'll just be the particle in the box Hamiltonian. And then you set the derivative of that expectation value with respect to that parameter that I'll tell you about. It'll just be like, you'll have a sine and a cosine of some angle theta or something like that. You'll take the derivative with respect to theta equals 0. And then end up, solving for, okay, what does theta have to be in order to satisfy that? So that'll be kind of a simpler, much simpler form of a variational, where you're actually using the variational principle. And so let's see what I'm doing. Okay, so this is probably, so hopefully if all goes well, then I hope everybody's on track to try to finish the second homework by Monday, I guess, if all goes well. And then after that, if you want to take a look at these problems right here. And what I'll do, I think maybe what I'll do, this is probably a good point for me to break off for right now. I'll just give you a little bit of a heads up again. What is the variational principle? The idea, so in the simpler version that I'll be talking about, not the BCS theory, the idea is that for the ground state, let's say this will be what we call a trial wave function. And so what you do is you set up your trial wave function such that there's some parameter embedded inside that. Like, basically what do you mean by trial wave function? It's literally a guess. You actually guess some form for your wave function, but you introduce a parameter. And so what's going to happen in the particle in a box version, which is going to be obviously much simpler than the BCS theory, is I will actually tell you, okay, let's try this wave function out. So what I'll do is I'll give you a particle in a box, and I'm going to throw in a delta function inside. Okay, particle in a box with delta function potential. And so I think what I am going to do is I'm going to be giving you a trial wave function where it's going to be something like a cosine function times, I think it was the original ground. So the original ground state was, you basically have and so I think, and then of course the second one is going to be and so what's going to happen is that I'm going to give you a trial wave function that's going to be, I'm trying to remember, I had it set up before, I have it typed out, but I forgot some of the details. I think it might be something like cosine of some angle times psi 1 plus the sine of theta times psi 2, or vice versa. I forget which way I had it set up. And so what's the idea then is that you're going to plug this form of your wave function, because what's going to happen is that this Hamiltonian is not just going to be the original particle in the box Hamiltonian, but it's going to also include that extra delta function potential inside there, which messes everything up for your original wave functions. And so the idea is that now what we're going to do is we're going to put this new trial wave function into computing the expectation value. And so for the full Hamiltonian, including that perturbing delta function potential. And so then what's going to happen is that when we take the variation, what's going to happen, we're going to essentially take the derivative with respect to theta equal to 0, like a max-min problem, of that expectation value. And so you end up solving for theta, essentially, for a particular value, for a particular form of this perturbing potential right here. And then after you've done that, if you plug that right back into that function back into your expectation value, that actually gives you an estimate. So then what happens is that with that trial function, when you take this expectation value, that gives you sort of an upper bound on what the ground state energy is for that system. And there was actually somebody who, I can't remember which one it was, but somebody a long time ago showed that with this type of variational principle, that the expectation value that you end up computing ends up being the upper bound for what's the highest possible value that that ground state energy can be. So the closer you are in your guess to your trial function, then the idea is that the closer you are to the actual ground state energy for the system, for actually solving for the ground state energy. And now, to my knowledge, I don't know if somebody's actually figured out how to do this for, to my knowledge, this only works for ground states. So like if you're trying to figure out what is the ground state for my system, then you can use this so-called variational principle. And so that'll be probably the next, I guess I'll go into more detail for the next lecture. And I might maybe next week sometime upload that homework, which will be conceptually probably a lot easier than this. This one's kind of intricate, more abstract. This one will be a little bit easier to visualize in terms of the homework topics on that. And so I think that's probably, I think, a good point to go ahead and break off for right now. And if you could find some material online without getting into too many gory details about the BCS theory, that would also help. And then take a look at my notes again, which I think should be on Blackboard, that talks about the BCS theory there as well.
So this one will be due, I guess, right after spring break?
So yeah, sometime after spring break, yeah, probably shortly after spring break. And yeah, we say Monday, maybe the Monday after spring break, something like that.